بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Okay, so today we are going to talk about the different type of pandas built-in visualization for descriptive statistics. So how you can visualize your data. So there are different built-in visualization with pandas. So we're going to see that with visualization usually we're going to use matplotlib library or seaborn library. But also pandas by itself, you can use the data frame to visualize some of its data using the plot function or the plot method, which inherently it uses matplotlib in the background. Okay, so as already mentioned, the pandas, it has already built-in plotting and visualization functionalities, which are basically also based on the matplotlib library in the background, which we are going to talk about in the next lectures. So we can have line, bar, and area plots. I'm going to show you these different type of plots. Distribution plots, like for example, histograms and box plots. There are also scatter plots, like these figures that shows the scattering points for X and Y axis. The pie charts, the hex bin plots, and the density plots. So we're going to talk about each of one of these different categories. So let's start by the simplest, the line, bar, and the area plots. So you can use dot plot. So this is a data frame. Okay, temperature, humidity, it's a data frame. And here, for example, if I use dot plot, it will make a time series visualization of the humidity, which is in blue, and the temperature in blue and the humidity in the orange color. So we just use the dot plot over here. And this one also dot plot, it's going to visualize a plotting. You can also add additional configurations, like for example O for visualizing the points, the data points on the plot. So here we don't visualize the data points, we use just the default plotting method. And here we can specify more attributes like the style of the data points and also the title of the plot over here in the top. There are so many parameters, and you can get back to the pandas documentation to check the different options available for the plotting method of a data frame. So this is a bar plot. It's another type of visualization. And this is different from histograms because histograms basically are used for data distribution. And this is used to visualize, for example, average values or the raw values as well. So for example, here I present the raw values of the wind speed in each hour. And here we present, for example, the average value. Okay, we use the dot mean function to present the average values of the different grades. And the area plot, this is also another visualization of time series or values of the data frame. Okay, you can use dot plot, and the kind here is area. So look, there are two different ways. You can use dot plot dot bar, or you can use dot plot and you put the kind here, or the type of the plot is equal to bar. So both are possible. Okay, look at this notation here, plot dot bar, and here we use plot kind equal bar. So they are equivalent notations of the method. And area plots, so this is the same plot as the wind and the temperature that we provided here, but using area plots. And the kind here is equal to area. Okay, you can choose this type of visualization depending on the objective, depending on how fancy is the visualization you would need. And another type is also for distribution of the data. Distribution plots, and basically here we have histograms and box plots. So the histograms here, what's the difference between the bar plots and the histogram? So the bar plots is going to show you the real values, the raw values or the average values, and here is going to show you the distribution of values. So it's kind of probability distribution. So this means the frequency, how many times the value 22.5 was repeated in the data set. Okay, and for this we can use dot plot and kind histogram. And if you don't specify the bin size, is going to make an automatic bean size. So the bean size is actually the range of values that we are going to have over here. So it will make a uniform distribution between the minimum value and the maximum value, and will divide it uniformly to have uniform bean sizes. But for example, I can say the bean size should be equal to 5 temperature values or 3 temperature values, and the histogram would look different. So this is for the temperature, this is for the wind speed, and we can observe the distribution here. It has different appearance than the distribution here. And we're going also to talk about the skewness. We talked about the skewness yesterday, about the distribution, okay? Yeah, here we have a left side distribution, yes, skewed to the left. Okay, another very important plot is the box plot, or sometimes we call it the whiskers plot. Yes, so it shows the value between the minimum, the maximum, and the concentration of the values between the 25th percentile and the 75th percentile, and the average value, and you have here the median value. Of course, here you can use plot kind equal to box to get the distribution of data between the minimum value and the maximum value. And of course, you know how to read this one. The outliers are outside of the concentration box, and you can get relevant information about where the data is located, basically, yes.
What is vert?
Where is this?
Vert, after color red.
Vertical, it means it's vertical. It can be vertical or horizontal.
Doctor, another question. Is the histogram of the previous slide right skewed or left skewed? Because
the tail is on the right side, right? So it should be right skewed left.
This is left. For me, you know, when I look.
So the tail is on the right side. So should it be right skewed?
In the way we've seen yesterday, you know. Let me,
It says the tail. Tail is on the right side.
okay. Yes.
This is right side.
The tail is on the left side. Yeah, okay, it's with respect to the tail. Yeah, you're correct, yes. Yes. According to the definition, yes.
tail on the right side is right.
Okay, so you can see this is the raw data and this is the distribution. So we can see that the concentration of data is in this part, and these are considered as outliers. So this is for the wind speed also. And these other type of histograms, you know, for temperature and relative humidity. Okay, another important visualization are the scatter plots, and they visualize the relationship between two numerical values. So here in the x-axis we have the temperature, and in the y-axis we're going to provide the corresponding point related to the relative humidity. So when we see this plot, how can we interpret it visually?
There's a correlation between humidity and temperature.
Does the correlation seems very high?
Not that much, but negative
Yeah.
correlation. Negative correlation.
So we have negative correlation. It means when the temperature increases, the humidity will decrease. But it's not very strong correlation because, as you can see, there is spreading, okay, widespread of the data points. And do you remember yesterday how did we find what was the value of the correlation? So 60%?
0.6.
0.6, yes, because we see it's not very, for example, for this point 22.5, I can have a humidity around 20 or a humidity around 70. So there is a lot of variation. When the variation is very high, so if I have perfect correlation, it's going to be like straight line. But if the correlation is not high, we're going to have the spread of the points, okay, widely in the graph. Okay. So of course you can change the different parameters, like for example the color here has changed. This is between the wind speed and the temperature. And we have seen a positive correlation here, which is moderate correlation between the wind speed and the temperature. Here we are visualizing three correlations: the temperature, the relative humidity, and the wind speed. So the wind speed here is going to take colors, okay, based on the colors.
So about the last one, sir,
Hmm?
how do we see the correlation between humidity and wind speed for the previous one?
Which one? This one?
Yes.
Yeah.
Both the y-axis. How do we see the correlation?
It's based on the colors. Look now, a very dark color, it means low.
Low wind speed.
Yes.
And very high.
Yeah, and this one means high wind speed. Yes. So yeah, the correlation we have discovered yesterday, there is no correlation between the temperature and the wind speed.
Wind speed.
Okay, so this is why you can find dark and yellow close to each other. Look, we have dark here and dark here. We have dark here also. So there is actually no correlation. I remember yesterday it was 0.08. Okay, so the correlation is very weak. It's almost there is no correlation between the wind speed and the other parameters. Okay, so the pie chart is a circular statistical graph to illustrate numerical proportions. And we can visualize, for example, here the pie chart to check the proportion of data into, for example, a data set. For example, here in the data set that I'm using, the DF data frame of the weather, I have 50% of the data coming from Riyadh and 50% coming from city of Jeddah. And here we use the plot kind equal to pi. But here you have to be careful about what data are you providing. Look, we are providing the value count of the city data in the data set.
Yes.
Okay, to be able to use so when to use the pie chart, first of all, you must have categorical data. Okay, here, what is our categorical data here?
Riyadh and
City.
cities.
It's not numerical data, it's a categorical data. So you can use it on categorical data with a limited number of categories. Usually, it's not recommended to use it more when you have categories numbers more than 7. It's going to be cumbersome. Cumbersome, yeah. Yeah. And you want to emphasize the contribution of each category over the whole data set. And of course, this category must be exclusive, completely independent, but all of them, they are exhaustive. What does it mean? They contribute to the whole picture. Okay, so these are the conditions. Now, all the data, they come either from Riyadh and Jeddah. So all the data set is the sum of these two data sets, but they are completely independent. So this is what we mean by mutually exclusive, it's the independence, and collectively exhaustive, they represent the whole data set. Okay, it cannot present partial the data set because 100% it means the whole data set that we are measuring here, the proportion. And look now, this is applied on the grade data set, and this counts the number of grades I collected in each year. So I can see I have more grades in 2018, in 2013 I taught only one section, and here I taught 2 sections. Okay, so I can see the proportion of grades over the different years. Okay. Hex beam plots, also they are very important, and they represent dense point variation between 2 numerical values. It's like a scatter plot, but this one is more useful. Why? Because the scatter plot, you can have concentration of the points very close to each other, and it becomes cumbersome. Now here, instead of having different points into the same place, we can actually play with the density. It means how many points I have at this location. So when you say like dark locations, it means we have a concentration of points. And white location or bright location, it means that we don't have big concentration. Look, for example, here we have 1, 2 points, 1, 2 points. So it seems that the concentration of points is within this area. So it's like a scatter plot, but it handles the overplotting of the points into the plot. Okay, and you can visually reveal the density of the points at a certain location. So it shows the variation in density of data points which is not apparent in traditional scatter plots. So that's an alternative of the scatter plots. It has a better visual clarity, and it's also customizable, allow adjustment in size and color of the represented density level effectively. Of course, this is how you can do it. So here we use the matplotlib. We don't use the pandas directly. And it's applied on weather, temperature, and also the relative humidity. And you can play with the grid size. So you have the notebook. You can play with the grid size and also the color if you want. And there should be other parameters as well that you can explore further. So we use the scatter plot, hex beam plot are also used to visualize the relationship between two numerical values in large data sets to understand the relation and the correlation between both. Okay, so here I put interpretations that I invite you to read carefully. So this helps you to, for example, if I ask interpret a plot of hexabeam plot, these are the different observations that you can extract from the plot. Here I provide them in detail, and you can read this carefully later. So this is an hex beam plot applied on the grade data set and shows the relation between the major exam and the total grade. So how can we interpret this one?
Seems that
We have like very strong correlation.
Yes.
Yes, look, it's almost, the density is almost linear.
Almost one.
Yes. We can see now, this is better than the scatter plot because the scatter plot will show all these points with the same density. But I can see, look at the dense point. It's kind of have perfect line on the density of the points. And this makes more sense, okay? And of course, I have some outliers here and there that represent some variations, okay? And this is why we have, I think, above 70% of correlation when we've done this, yeah. So you can see this type of plots can give us very good insights about our data and having a better understanding about the information about our data. So make sure to have good grades in the major exam, okay? And you can predict, this helps you to predict your total grade at the end. Yeah, there is, you must use your data science now to predict your grade.
To drop the course.
No, you don't need to drop, at the end, regardless of the grade, the most important thing, the outcome is knowledge and learning. Yes.
Speaking of examinations, we discussed that we can do the final exam on an early date.
Yes.
So since we have all the students here, do you guys agree with this?
Which date?
On an earlier date than the PSU gate, it's.
Let's continue. Okay, now the last plot is the density plot, or also we call it the KDE plot. Okay, and this is similar to histogram, but it's a continuous function. And this is what we call it usually the kernel density estimate. Kernel density estimate, the KDE. So this is how we plot it, kind equal to density. And we call it density because the sum of this area that is below this curve is equal to 1. And this is the property of a probability density function. Do you know what is a PDF? Probability density function. The sum of the area in the probability density function is equal to 1. Okay? And this is basically like histograms, but it's a continuous function and offer a clear view about the distribution and the peaks of the data. And also it's able to identify patterns. Like for example, you will be able to identify patterns of irregularities in the density of distribution of the data. So what to use the density plot to understand the distribution of a variable in a data set, and when you need a smooth and a continuous estimation of the distribution. So we can do that using histograms or also the density plots or density kernel density estimate. Yes.
It's called density because it's a density function.
Yes.
Right. So, but is it kernel related to the operating system kernel?
No.
Something
No, it's something different, yes. It's related to the kernel that we talk about in AI and in data science.
It's another kernel.
Yeah. Okay, so how to interpret a probability density function? So first of all, we need to look when you have a probability density function, and I ask you, for example, interpret this KDE. So first of all, you look at the peak of the distribution, this is the peak. So the highest point on the curve represents the mode of the temperature data. So this represents the temperature data, which is the most frequent value where the data is most concentrated. This is the mode. The most frequent value is here. So I think we identify it to be around
27.
26 or 27, yes. So the peak suggests the most common temperature range experienced in Riyadh. And also the spread of the distribution, the width. So what does it inform us, the width? The variability of the data. If I have wide KDE, it means I have wide variety of data, okay? And shows the variability of dispersion of the temperature data. A wide curve would indicate more variability in the temperature, while a narrower curve suggests less variability of the temperature. The shape and the symmetry. The curve seems to be slightly skewed to the right skewing, okay, the tail from here, which indicate that temperature distribution is not perfectly symmetric and has stronger tail to the right.
Right.
Yes.
Right.
This means that some days with temperature significantly higher than the other. Okay? في عندنا temperatures that are higher, that are more frequent. Okay, the tail of the distribution, the tail of the KDE extends toward the lower, higher ends of the temperature, and also the bandwidth. It means the smoothness of the curve is determined by the bandwidth of the KDE. A higher bandwidth will result in a smoother curve, while a lower bandwidth might show more fluctuation, indicating minor variation in temperature frequency. Okay?
Do you have to know each point, like what it's supposed to mean?
Yeah, usually these 3 points are the most important. The peak of the distribution, this is the concentration of the points, the spread, variability of the data, okay, and shape of symmetry. You can see that all these different representations, like the box plot, the scatter plot, the hex beam plots, they give us similar information but from different perspectives. Okay, so these actually they consolidate each other. So usually you can use only 1 or 2, 3 depending on what you would like to analyze. Okay, so the last part here is about smoothing time series data and plotting functions. So look now, imagine that you have this weather data. And you know that raw data is usually fluctuating. Sometimes they can have up and down values. And in time series, every time or every hour you have a certain raw data value. And you would like to make, for example, a prediction or an estimation of the temperature over a certain amount of period of time. And this is how we usually represent raw data. We can represent them as plots, okay, time series plots, or area curves, or also bar plots. But this data is actually looking noisy. Look at the peaks here. Look at the humidity. Sometimes there are fluctuations. It's not smooth. Okay? We have up and down, up and down. Maybe the humidity has more variations during a day as compared to the temperature. And this variation actually, it doesn't help to estimate or even to make a prediction in the future about what could be the relative humidity. So this is what we call actually a noisy data. A noisy data is when it has a lot of fluctuation. It's not consistent. It has a lot of up and downs. And we use smoothing, and I will show you 3 different techniques on how to smooth that data. To reduce the noise, smoothing helps to reduce the random noise that we can get here. Enhance the signal, it makes gain-one pattern that is more noticeable by averaging among the fluctuations. So how we reduce the fluctuation? I'm not going to take the raw data, but I'm going to make an average over a certain period of time. Instead of taking 5 different values, I will take the average of these 5 different values. So this is going to reduce averaging, reduce the variability. And this is why when you have a large population of data, it's completely random. If you take the average value, it's going to be only one value. But this value is not exact, it's just an estimation of the sample. And it is complemented by the standard deviation of the variance to know about the variability. So the idea of smoothing is to get short-term averages. Okay, not long-term averages. Short-term averages test to reduce the noise. If the noise is very high, I can increase the window, or if the noise is very low, I can decrease the window. Yeah.
The bigger the numbers, the more misleading the average is.
Yeah, you smooth more, of course. If you increase the window size too much, it's not going to be representative of the data. You're going to just have value that is constant. But it's a hyperparameter. This is what we call a hyperparameter that will affect the smooth. And a hyperparameter, you know, it's basically trial and error. It depends on the objective of the study. So there are different criteria on how to choose the hyperparameter. And I'm going to show you some examples here to understand better and simplify the analysis. I don't need to care about the fluctuation, but I need to know the overall trend of the data. Imagine that you want to see the trend of the data. Is this data decreasing or increasing? So I can make a prediction. Now, like this, it's too much fluctuating. It's very difficult to discern the pattern. I cannot extract any pattern. It's too much fluctuating. Also, this one, is it slightly decreasing or slightly increasing? I know it's varying, but it could have a pattern. So to understand the pattern, we can use smoothing. Look now, this is the original temperature pattern, and I have three different ways on how to smooth. The first way is called the moving average or the rolling average, and we use the dot rolling, and we provide a window size. So, for example, here, this is the raw data plot, and the orange plot. Look at the orange plot. This, I'm taking the average of the temperature over 24 sample data, and since I'm measuring by hours, it means I am averaging over a day. So I get the average of a day, and look now, the average of the day has less fluctuation because the temperature from one day to another is not fluctuating too much. Look in Riyadh, for example. You get up in the morning, you have 7 degrees, and in the afternoon you have 25 degrees. And if you measure this during the day, you're going to find a lot of fluctuation, up and downs. But if I look, for example, what is the temperature in Riyadh today? I will take the average, and that's represent my temperature. Tomorrow, I'm going to have a different temperature, but not very far from the current one. So I reduce the fluctuation. So if I want to make a prediction, what will be the temperature after 5 days? Will you take the hourly data or the daily data? Yeah, daily data. And this is what you do. This is the rolling average. I'm going to average all the temperature data over a day, and I will consider that as my window. واضح? Okay, look now, and I can see that there is a trend that is decreasing. Still, we have fluctuations, of course. I can smooth the fluctuation more. If I make it over a week, if I make it over a month, I can have less fluctuations. But the trend here is decreasing. Okay? And another way is to do expanding. And so expanding calculates from the startup to the current point, expanding the window size each time. I will show you the different calculations, how we do them. And the expanding is the green light. Look, it's another curve. And we can have, this is very popular, exponential moving average. Okay, and also we specify a time period. And this is actually the red curve. Okay, and here also we span over 24 hours. Look now, for the rolling average, how do we calculate it? For example, I take a rolling average, window equal to 4. So what I will do, this is my sample. This is my data here. So I'm going to skip the first one. I will start to calculate from index 3. So I'm going to do 1 plus 2 plus 3 plus 4 divided by 4. And this is the average, 2.5. Then I will take the window from 1 to 4. Okay, so I will calculate from 2 plus 3 plus 4 plus 5 from here. And this is going to give another average. And then I will calculate from 3. 3 plus 4 plus 5 plus 6, and I will take the average. So this is called the rolling average.
But on what term are you choosing for? On what assumption are you using for?
No.
Well, that is just an example.
No, this is just the window equal to 4. Now I'm explaining you the calculations for a window equal to 4.
Okay.
Yes. And this is the mathematical equation. Okay, if you have so n, the size of the moving window, I divide by n, size of the moving window, and we're going to make the sum of the values between t minus n plus 1 plus until t. So here I will always have n value, the sum of n values, and then I divide by n. And this is, we call it the moving average. Look, I take the first window average, then I move to the next window, I take the average, and then the next window, I take the average, and then the next window, I took the average. واضح؟
The window is taken based on the assumptions. If it's a temperature,
It's a hyperparameter, you choose it.
you choose.
مثلا أنا في temperature I have hourly connection, so I would like to make it over 24 hours. Maybe I want to make it over 2 hours or 1 week.
Okay.
So you decide, depending on how fluctuating is your data and what is your objective, what is the objective of the study. Okay, and these are some different examples. Okay, for example, we can move from this one to this one. You have all of them in the notebook, so you can play with them. We have also expanding, and this is how we do expanding. Look now. I will measure, for example, 1 plus 2 plus 3 plus 4 divided by 4, and then 1 plus 2 plus 3 plus 4 plus 5 divided by 5. So I will expand the window each time by 1. Okay? So this is going to take the whole history. So the first one is you have a short memory, or you take the short history. The second one, expanding, is going to take the overall history. So everyone has its pros and cons. This one at the end is going to converge like to a constant value, لأنه الهيستوري بشي أكثر على الأفريج. الأخرى غالبا تكون أقرب للواقع على الشورت term. Yes. At the end it's a sum. Okay, but this sum is going to be mostly a constant now. If we see here, look, شوف الأخضر. فالأخير it's converging to a constant value. لأنه ياخذ كل المجموع بتاع السابق كامل. فلو مثلا ناخذ if I make the computation based on a history of 100 years, I'm not going to, it's going to be almost the same because the average is going to be affected by the history more than the current value.
Yes.
Okay? And this is why like rolling average is more common, or also we can use EWMA, which is the exponential weighted moving average. And we can move from a fluctuation like this to the red curve. Okay, and this is how we calculate it. It's a simple moving average. This is the simple moving average. This is the weighted moving average. So here I'm going to give a weight to the history. Okay, which what does it mean? It means that the current value has more weight than the previous values. It's going to decrease by 1. Look. If n equal to 5, the first value is going to take a weight of 5, then a weight of 4, then a weight of 3. Yes, so I will make more emphasis on the recent value more than the history values. Okay, this gives a weight equal to, it's 1, the same weight for all. Now here I'm going to make different weights depending on the history, and this is the exponential weighted moving average. Is going to equal to y1, okay, for t equal to 1, and will be just a weighted sum of the past plus of the present plus the past. And here alpha is a hyperparameter. Okay? Yes. So if you want to give more importance to the past, what we should do? We should decrease alpha. If I want to give more importance to the present or to the current state, I will increase the value of alpha. So alpha is a hyperparameter that lets you choose what will be the weight of the present and the weight of the past in your calculations.
If you don't want any weight, you make alpha 0.
Yes.
Okay.
This is what we call the degree of weighting decrease, okay, which is a constant smoothing factor between 0 and 1. And here we have 3 types: com, span, and half-life. And these different types depend on the way on how to calculate the value of alpha. Yes. Okay. We already finished now.